This is STM32F103 datasheet, and we're going to talk about what are peripherals and why do we want to change the register's value. In page 11, you see block diagram of our microcontroller. Main parts of a microcontrollers are CPU, which runs the code, memories like flash, which we store code in it, and RAM for variable storage. We have also buses that can pass data between different parts of the system, and we have peripherals. Peripherals are electrical circuits designed to do specific tasks, which is mostly about sending or receiving some form of data. This data could be of type Boolean, like a state of a GPIO pin. For example, configuring pins in input or output mode, or changing pin state in output mode, or reading pin state in input mode is done through GPIO peripherals. Each GPIO peripheral can control up to 16 pins. So how can we tell peripheral what do we want to do? We're going to use blink example. This is blue pill schematic, and we're going to make the green LED blink. Anode of the green LED is connected to VCC and cathode is connected to PC13 with the resistor. So if we want this LED to light up, PC13 should be ground. So when our load is active, PC13 should sink current. So either push-pull or open drain configuration are acceptable. For configuring PC13 in output mode and changing its state, we need GPIO-C peripheral. This is STM32F101-105 reference manual. 9.5 GPIO and AFIO register maps. Table 59 GPIO register map and reset values. Each peripheral has a set of registers. In our microcontroller, peripheral registers can be 16 or 32 bits. Each GPIO peripheral has 7 32-bit registers. For each pin, we have 4 bits for specifying the input or output configuration. The first two are called mode and the second two are called CNF. Each GPIO peripheral is responsible for 16 pins. So 16 times 4 would be 64. And we have two 32-bit registers for that. Port configuration register low or CRL is responsible for pin 0 to pin 7, and port configuration register high or CRH is responsible for pin 8 to pin 15. So for pin 13 of GPIO-C peripheral, we need to configure these 4 bits, which are mode 13 and CNF 13. We have to figure out what should we write in these bits. So go to 9.2 GPIO registers. Page 172, port configuration register high, GPIO-C CRH. First, we're going to talk about mode. Mode is 2 bits, and if we write 1, 0 or 2 in it, we get output mode with 2 MHz max speed. So what about CNF? We are in output mode. It has to be general purpose, but it can be push-pull or open drain. So it can be the first two. But I'm gonna choose open drain because in this situation, we don't have to change CNF bits. Because the reset value for CNF bits is 0, 1. We're gonna go back to register maps. As you can see, the reset value for CNF bits is 0, 1, so we don't have to change it. But the reset value for mode is 0, 0. And we need bit 21 to be 1, so we had to set bit 21 of GPIO-C CRH register to configure PC13 in output open drain mode. Next question is, how can we change output state of PC13? We can use ODR, BSRR or BRR registers. We're going to use ODR. 9.2 GPIO register and page 173 ODR register. ODR 13 is associated with pin 13. If you set this bit in GPIO-C ODR register, PC13 would be high or 3.3 volt. If we clear this bit, PC13 would be low or ground. Going back to register map, we know we have to change content of ODR and CRH register of GPIO-C peripheral. But where are these registers? To calculate address of a register, we have to add offset of that register and peripheral base address. Peripheral base address is address of the first register of that peripheral, and offset is the distance between a register address and base address of that peripheral. For finding base address of each peripheral, we need memory map. 3 memory and bus architecture. Page 50, 3.3 memory map. In table 3, you can see boundary addresses for different peripherals. The first address that you see here is base address of this peripheral. It means it's the address of first register of this peripheral. For port C or GPIO-C peripheral, we can see the base address here. Now we can calculate address of each register in GPIO-C peripheral. But before we start changing those registers, there is another thing that we have to do, and that's enabling GPIO peripheral clock. For that, we need APB2ENR register from RCC peripheral. 7311 RCC register map. RCC is a peripheral responsible for microcontroller's clock, and it has 3 registers for enabling or disabling other peripherals clock. There's a register called APB2ENR, and bit 4 of this register is for enabling or disabling GPIO clock. If you set this bit, GPIO clock would be enabled. If you clear this bit, GPIO clock would be disabled. Also, for finding address of this register, we had to add the offset of this register and base address of RCC peripheral. First of all, we need somewhere to put our projects. I'm gonna make a new folder here and name it. Open STM32 Cube IDE software. I'm gonna make this folder here our new workspace. Click on Start New STM32 Project. In target selection page, we have to write our microcontroller's name in part number box. We should choose it from here and click Next. I'm gonna name this project 1, it's not important. The important part is that you select empty as targeted project type and click Finish. This is our project. The source folder has main in it. We don't need this and we don't need this. For making this a little bit bigger, click on Windows, Preferences, General, Appearances, Colors and Font, Basic, Text font, edit this. I'm gonna make this 16. Okay, apply and close, and we have this bigger. Can minimize these views. I'm pasting a comment here. This is a table of things that we have to do. We have to set bit 4 of a 32-bit number that is in this address. This 32-bit number is APB2ENR register of RCC peripheral. And we are setting this bit because we want to enable GPIO peripheral clock. We had talked about other things. And bear in mind, this project has the minimum requirement for uploading a code to our microcontroller. And now we don't have any file or software layer to facilitate peripheral register access. Click on Flash next to debug. We need to make a new debug configuration. Double click on this. The right ELF file is chosen here and click on debug. Now we are in debug perspective and you can see the microcontroller here. We need SFRS view. If you couldn't find it here, you can find it in Window, Show View, SFRS. In SFRS, we have Cortex M3 and STM32F103. These are CPU peripherals and the others are microcontrollers peripherals. We can minimize this. First, we have to set bit 4 of RCC APB2ENR register. RCC peripheral is here. You can open this. APB2ENR is here and click on bit 4, IOPCEN bit. Now all bits are visible here. If I click on this, I can change the state of this bit. It was 0 and now it's 1, and I can turn it to 0 again, and I can make it 1 again. So you can change peripherals register's value just with SFRS view. Next, we have to set bit 21 of GPIO CRH register. GPIO CRH register mode 13. This is bit 20 and this is bit 21. Pay attention, when I set this bit, what happens to this green LED? I set this bit, as you can see, green LED is turned on. Because PC13 is an output configuration now and its state is low, so LED is on. Then we go to ODR13 and we can turn LED off by setting bit 13. I set this bit and LED is off. I can turn it on or off. On, off. But this is not a useful method because we need to change peripheral registers in our code, not in SFRS view. We know in this address there is an unsigned 32-bit value that we have to change. For this we need a pointer. Pointer is an expression. It means it has a value and a type. Pointer value is an address. All addresses are 32-bit unsigned values. Imagine we have a pointer value named PTR and I change its value to APB2ENR address. If we put asterisk before PTR, now we can access what's in this address, which is the value of PTR. If we put asterisk pointer behind assignment operator, we're going to write in this address. And if we put it somewhere else, we're going to read from this address. Now I'm reading content of this address, I'm adding it to 1 and storing it in this address. Asterisk PTR is an expression. It means it has a type and a value. So what do you think its type should be? We are reading value from APB to ENR register or writing value to it. What is the type of this value? Because this is a 32-bit register, the type of value should be unsigned int or uint32, which is unsigned 32-bit value. So we need to specify what asterisk PTR type is going to be. Before defining our pointer variable, I'm going to define some regular variables. Before main function, first you write variable type. After that, one white space is mandatory. Then you can write variable name or a list of variable name. It means A and B are variables, both have 4 bytes in memory with unsigned 32-bit values. Next, I'm going to define a variable of type int16 and I'm gonna name it C. It means C is going to have 2 bytes in memory with 16-bit signed value. So what about our pointer PTR? So before PTR we have to write its type, but compiler already knows what PTR is because it's going to be a pointer and all pointers are 32-bit unsigned values. What compiler doesn't know is what do we want the type of asterisk PTR to be, and that's exactly what we're going to specify in pointer definition. Our pointer name is PTR. In pointer definition, first you have to write what's going to be the type of asterisk PTR. In this situation, we want asterisk PTR to be of type uint32t. Then one white space is mandatory. Then you have to put asterisk or dereference operator. And after that, you have to write pointer name, which is PTR. Between PTR and asterisk, there could be spaces or not. So what's going to be the type of PTR itself? Type of a variable is written before that variable in definition of that variable. This is definition of PTR and this is PTR. Before PTR we have uint32t asterisk and this is the type of PTR. Now we have our pointer and we can read or write 32-bit values in APB to ENR address. But our goal is to set bit 4. How can we do that? First, you have to know about bit mask. Consider RCC APB to ENR, which is a 32-bit register. Bit 4 of this register is IOPCEN bit. IOPCEN mask is a 32-bit value where all bits except bit 4 are 0. We can make this value, the mask value, with the left shift operator. We write 1 left shift 4. At first 1 is here, then 1, 2, 3, 4. It's shifted to left 4 times. We use this number to set or clear bit 4. For changing any bit, first we need its mask. We want to set bit 4 of a register, but we don't want to change other bits. So first we have to know what is the value of that register. Then we have to change it and then save the new value in the register. For changing the value, we're going to use bitwise OR operator. This is a 32-bit register and this is a 32-bit mask of bit 4. For setting bit 4 of this register, we're going to bitwise OR value of this register with value of the mask of bit 4. All bits in register except bit 4 are ORed with 0. Whatever x is 0 or 1, when it's ORed with 0, result would be x unchanged. But bit 4 is going to get ORed with 1. And whatever this x is, when it gets ORed with 1, the result would be 1. Then we save result of this operation into register. We write this in C like this. Register bitwise OR mask. Then we save the result of this operation into register itself. We can write this also in this form. Register bitwise OR equal mask. For clearing a bit, we need reverse of bit mask. For clearing bit 20, we need a value with all bits 1 except bit 20, which must be 0. For making this value, we use bitwise NOT operator on bit mask, which reverses all bits. We bitwise AND this value and register value. All bits of this register except bit 20 get ANDed with 1. And result would be bit unchanged. But bit 20 is ANDed with 0 and result would be 0. So for clearing a bit, first you bitwise AND the register value and not of bit mask. And then you save the result in register itself. You can write this also in this manner. Register bitwise AND equal not mask. So for setting bit, you use bitwise or equal mask. And for clearing bit, you use bitwise and equal not mask. Our pointer is holding APB2ENR address. For setting bit, we write asterisk PTR, then we write bitwise or assignment operator, and then we write bit mask, which is 1 left shift 4. And that's how we set bit 4 in this address. Next step is replacing our PTR. PTR is a variable pointer which is holding APB2ENR register address. But this address is not going to change and we don't need a variable pointer. We are going to write a constant pointer in place of PTR. Remember, pointer is an expression, whether it's constant or variable. An expression has a type and a value. The two things that we have to know about PTR. In place of PTR, I put parentheses. This parenthesis is going to contain our new expression, which is a constant pointer. First, we write pointer value, which is PTR value, which is APB2ENR address. For specifying type for this value, we have to do something called casting. For casting, I put a parenthesis before this value. And in this parenthesis, I write type of this expression, which I want to be the type of PTR, which is uint32t asterisk. I write type of my pointer in a parenthesis before value of that pointer, and I put that in a parenthesis. This is our new pointer, which is constant and has the same type and value as our variable pointer. We don't need PTR or these variables anymore. For making this line more readable, I am gonna add some definition. This definition means wherever in code we write RCC APB2ENR is going to be replaced with our asterisk pointer. And with this definition, wherever in code we write RCC APB2ENR IOPCEN, it would be replaced with 1 left shift 4, which is what we want. After APB2ENR, we have to change CRH. This is our pointer to access CRH register. This is CRH address and this is type of our pointer. We put asterisk before our pointer to access register. For clearing bit, you do bitwise and assignment with not of bit mask. We want to clear bit 20. Its mask would be 1 left shift 20. The next thing is setting bit 21. I make this 2021. We don't need to reverse it, and this is going to be bitwise OR. For setting bit, you bitwise OR it with bit mask. Next, we're going to set and clear bit 13 of ODR register in our infinite loop. This is ODR address, and this is our pointer that we need to access ODR register. And for accessing ODR, we use asterisk pointer. For setting bit 13, we do bitwise OR assignment with bit mask. And for clearing bit 13, we do bitwise and assignment with not of bit mask. If we want blink LED to be visible by naked eye, we need a delay function. This delay function is just a nested for loop. We're going to call delay function here and here. I'm going to compile the code. We don't have any error and warning, and then going to debug perspective. Go to SFRS view. First, we need to see RCC APB2ENR register IOPCEN bit. Now you see this bit is 0. If I pass line 24 with a step into or a step over, you see this bit would be 1. This line set this bit. Now we go to GPIO CRH register and mode 13. Mode 13 is now 0, 0. But when we pass this line, bit 20 would be 0, and bit 20 is 0 right now, so nothing would happen. After passing this line, bit 21 would be 1. I pass this line, 21 is 1. And now LED is turned on. Then we go to ODR register. ODR 13, I'm gonna step over line 31 because I don't wanna go into function delay. I'm gonna step over this line too, and as you can see, ODR 13 is changed and LED is off now. If I step over function delay one more time, I reach line 34, and if I step over this line, this bit would be 0. This was first way of accessing peripheral registers. In this method, we had to make a pointer for each 32-bit register. For next method, we're going to use a structure. GPIO peripheral has 7 32-bit registers that occupies 28 consecutive bytes. We can consider GPIO peripheral registers as a structure with 7 32-bit unsigned members. To access this imaginary structure, we need a pointer. This pointer need a value and a type. Pointer value would be address of this structure. Address of a thing is address of its first byte. So our pointer value would be GPIOC peripheral base address. To define a structure type in C, first write type def. Then we specify our structure type. For that, first structure keyword, then structure members in curly bracket. This structure type has 7 32-bit members. Then our new type name. We are doing two things here. First, defining a structure type. This is a type and we can define a structure variable with this. Second, defining a new type based on our structure type with type def. Our new type name is GPIOT. We needed this type to make our pointer. Next, we're going to make a pointer to access GPIOC peripheral registers. To make a pointer, first we write its value, which is GPIOC peripheral base address. Before that, I put parentheses to cast this number and specify its type. To write pointer type, first you write asterisk pointer type, which is GPIOT. Then we put asterisk. This is our pointer, and if we put asterisk behind it, we can access a structure of type GPIOT that is in this address. We want to access CRH or other GPIOC peripheral registers as a member of a structure. To access a structure member, we have to put our asterisk PTR in parentheses and put dot operator after that. We want to access CRH and we know it is GPIOC peripheral second register. So we choose X2. This is access to CRH and we can bitwise OR this with bit 21 mask to set it. We can also change X2 to CRH to make our code more readable. And I can delete X2 here, and now if I press Ctrl space, I can choose CRH. I did it for other registers as well. This structure type is designed according to GPIO peripheral registers. Next step is using arrow operator. This is our pointer. Instead of putting asterisk operator behind our pointer, putting them in parentheses and putting dot after them for accessing structure members, we can just use arrow operator. This is our pointer, and when we have pointer to an structure, we can put arrow operator after it and then we can access structure members. I'm going to choose CRH. Then I add definition of our pointer. This means wherever in code we write GPIOC, it's going to be replaced with this, which is our pointer. So instead of our pointer, we just write GPIOC. A standard CMC layer works like this. We also have to clear bit 20 in this register. Now for accessing a peripheral register, first we write peripheral name, which is GPIOC. Then arrow operator and then register name. For clearing, bitwise AND it with not of bit mask. I'm gonna comment these two lines. We have to do this for ODR too. First we write peripheral name, arrow operator, and then register name. And this line would be for clearing bit 13. Compile the code, no error or warning. And then loading the code, and it is blinking, trust me. With the tools that we made, we are able to write peripheral name and then arrow register name. And we can access a 32-bit value. For changing bits, we need bit mask and bitwise operators. In these two lines, we are changing content of mode 13 bits of GPIOC CRH register, which are bits 20 and 21 of GPIOC CRH register. I want you to just imagine, wouldn't it be great if we were able to just write mode 13 here, and just with assignment operator and without any bit mask we were able to change content of our desired bits. It is actually great and we are able to do this. Until now CRH was an unsigned 32-bit member of GPIO type. Now CRH has to have its own members. So we have to design a type according to CRH register. CRH is a 4-byte 32-bit register that has 16 2-bits. What is a 32-bit type that has 16 2-bit members? This is a structure with bit field. Starting from bit 0, first member should be mode 8 with 2 bits. Then CNF8 with 2 bits. And last bit field should be CNF15 with 2 bits. We are going to design a structure this time for CRH. We have to do it before GPIO type. First type def, then struct, then in curly bracket we're gonna define structure members. To define a bit field member, first we write its type, then one space is mandatory, then its name, then colon, and then we're going to specify how many bits we want this bit field to have. It's going to have 2 bits, then semicolon. And also before all bit fields you have to add volatile. One might ask, if our bit field is 2 bits, why should its type be uint32t? Because bit field type specifies its alignment and if it's signed or unsigned. I wrote other bit fields according to CRH register. Then we have to name our new type. I name it CRH type. Sum of all bit fields is 32 bit and CRH type is a 4-byte type. In next step we have to change CRH type to our new one. Now CRH is a structure that has 16 bit fields, each 2 bit. Now we have to use it. I'm gonna comment these 2 lines and I'm gonna delete this. Now for accessing a bit and changing it, first we write peripheral's name. Then arrow operator. Next I'm gonna choose register and I know this is a structure now. So I can access its member which are bit fields. After I put dot after CRH, I can access this structure member. I'm gonna need to change mode 13. I don't need bitwise operator anymore. I can access bit 20 and 21 just with assignment operator. And we also don't need bit mask anymore. So we gained something. Now we can access bits. But what if we wanted to access our peripheral in a 32-bit manner? We can solve this problem with union. CRH shouldn't be a structure. It should be a union. I'm gonna define a new CRH type. This is going to be typed of union. Curly bracket, and we're going to define its members. Union is like a structure, but all of its members have the same address. This union has a member of type uint32t that we're going to call reg, and has a member of CRH type we're going to call bit. And this is going to be CRH type v2. This is going to be CRH new type. Compile the code. CRH is not a structure anymore with mode 13 member. It's a union. If we put dot after CRH, we're going to access its members, which are bit and reg. Both of these have the same address. This is union application. We used union because we wanted to access one address as 2 types, as a structure to access its bits or as an unsigned 32-bit. So I'm gonna access its bits. Bit itself is a structure, so we can access mode 13 and we can change it. Now I'm gonna compile the code and there is no warning or error. So far we've defined 3 new types. GPIOT, which is a structure we needed to make our pointer. CRH type v2, which is a union type for CRH member, and CRH type for bit, which is a structure with bit fields. We can integrate this last 2 in GPIO type. CRHTV2 is actually a new type name for this union type. We can write original union type in place of CRHTV2. This is a structure member definition, this is a structure member type, and this is a structure member name. CRHT is a type name too, and original type is this structure. I'm gonna put it in place of CRHT. We integrated these 2 types and we don't need them anymore. Next step is doing what we did for CRH register for ODR register. So ODR type is going to be a union. We're going to define its member in a curly bracket. First member is going to be of type uint32t and we're going to call it reg. Second member is going to be a structure with bit fields that we're going to design according to ODR register. Reference manual, page 173. If we start from bit 0, first bit field would be ODR 0 with 1 bit. Second would be ODR 1 with 1 bit. And last would be ODR 15 with 1 bit. I'm going to design a structure based on this register. First we write volatile, then bit field type, which would be uint32t, then bit field name, which is ODR0, colon and number of bit, and then semicolon. I wrote other bit fields according to ODR register. This structure is a union member type. We're going to name this member bit, and our union name would be ODR. Next we're going to use this. To change ODR register, First we write peripheral name, arrow operator, register name. Now ODR is a union. We put dot after it. We can access ODR as a 32-bit or we can access its bits. So bit itself is a structure and we're going to access ODR 13 and we're going to write 1 to it. To replace this line, we wrote this line. And for clearing bit 13, we're going to write this. Another great thing happened in our code. Now this value has a meaning. When we write 1 here, it means we're going to set bit 13. When we're writing 0 here, it means we're going to clear this bit. But bit mask doesn't have any meaning because we use it for setting or clearing bits. And these are two different meanings. So what difference does it make? I'm gonna add some definition here. This is definition of bit 13 mask. Instead of bit mask, we can write this. But this is not specifying what we're going to do with this bit. We can use this wherever we need bit 13 mask. As you can see, you don't know what you're going to do with this definition. You might want to set a bit or clear a bit. But what about bit fields? I can use this definition for setting bit. Instead of 1, I can write my definition. And this is a meaningful definition because we know what we're going to do with this bit. We're going to set it. And we can use this definition for clearing bit. I can paste it here. This is also a meaningful definition because we're going to know what would be the purpose of this line. Comment these two and compile the code. No error and warning. Last part of this video would be about CRH register. I want to put PC13 in output push-pull mode. We need to clear both CNF bits, which are bits 22 and 23 of CRH register. For changing CNF, first we write peripheral name, which is a pointer. After pointer, we put arrow operator. I choose CRH, which is a union. I choose bit, which is a structure with bit fields. Now I want to access CNF13 and I want to clear both bits. To change mode 13 and CNF13, we need these two lines. I want you to think about a way to do this task, but with half of work that we're doing now. Think about a way to change mode and CNF in just one line. Keep in mind, for configuring each pin, we have to configure 4 consecutive bits. The lesser significant two are called mode and the other two are called CNF. We don't have to care about mode or CNF. It's just 4 bits for each pin. Instead of 16 2-bit, we are going to have 8 4-bits. For each pin, we have to config 4-bit. I'm gonna call MONF. Next step is changing this structure that we designed according to CRH register bits. Now instead of having CNF8 and mode 8, we're going to have MONF8, but with 4 bits. And we're not going to have a CNF anymore. I changed other members too. Now instead of accessing mode and CNF in 2 different lines, we can access MONF in one line. First we write GPIOC, then CRH bit. Now we can choose MONF13 and we can write value to it. But what should we write in MONF bits? We just have to put CNF and mode values together. When mode is 01, it means pin is going to be in output mode with 10 MHz max speed. CNF also can have these values, each with their own meaning. If CNF is 00 and mode is 01, MONF is 0001. And we have general purpose output push-pull with 10 MHz max speed as our GPIO configuration. We put them together and we have 15 MONF values, each representing a specific configuration for a GPIO pin. Now we can forget about mode and CNF. We just have 4 bits called MONF. These are MONF values in binary and hex. Next step is writing definitions for MONF bits. These are MONF bit definitions. First, peripheral name, register name, bit name. You need this because it makes your definitions organized and easy to find. Then we put 2 underlines. Now we can describe what this value means. If we write this value to MONF bits, what our GPIO configuration is going to be. If we write 1 to MONF bit, our GPIO configuration would be general purpose output push-pull with 10 MHz max speed. For PC13, we want it to be general purpose output push-pull with 2 MHz max speed. For this, CNF13 must be 00 and mode 13 must be 10. So MONF13 must be 0010 or 2. In place of 2, we write this. This is the value that we have to write to MONF bits to get general purpose output push-pull configuration with 2 MHz max speed.